Okay, we need to wrap up relativity pretty soon, so I should move on to the velocity transformation just real quick. Remember when we did the Galilean transformation, we had x equals x minus vt, and we wanted to find the velocity transformation. We just took the derivative, time derivative both sides, right? So I can take the Lorentz transformation, and I could take the time derivative to look at the velocity transformation, time derivative again to look at the acceleration transformation, etc. We're just going to look at the velocity transformation. So let's go ahead and take the time derivative. If I take the time derivative of the first equation, we get dx prime dt is equal to gamma, right? Take the time derivative of the right-hand side. Gamma is just a constant, remember? So taking the time derivative of the right-hand side, we get the first term, dx dt minus v. So dx prime dt equals gamma, and dx dt would be u, right, the velocity of an object in the unprimed frame, minus v, the velocity of the frame. Okay, so we get u prime equals u gamma minus v. Now, hopefully somebody saw that I just did something wrong. Right? This is incorrect. Wrong, wrong, wrong. Why is it wrong? Because this is not u prime. This equation is correct, but that kidney bean shaped thing on the left is not u prime. Tricky, tricky, tricky. Right? What would u prime be? U prime would be, right, so if u, the velocity in the unprimed frame, is dx dt, then u prime, the velocity in the prime frame, is dx prime dt prime. Remember the fact that the whole point of relativity is that time is no longer absolute. So we've got to take the time derivative within that frame. So how do we do that? Well, it's actually not that hard. What we have to do is we have to take a slightly closer look at these two equations. If x prime is equal to gamma, so we can just write these two equations meaning the top two equations. So we can just write this as a differential. Dx prime equals gamma dx minus v dt. It's just like writing it as a, delta x prime equals gamma delta x minus v delta t. And we can write this as dt prime equals gamma t. dt prime is gamma dt minus v dx over c squared. All the rest are constants. So therefore, dx prime dt prime, which is u prime, is equal to gamma dx minus v dt divided by gamma dt minus v over c squared dx. And so, what was I going to say? Careful about your algebra, right? U prime. The gammas cancel, but nothing else cancels. But I'm going to go ahead and divide top and bottom by dt. So I'm going to divide out the gammas and divide top and bottom by dt. So we've got dx dt minus v over dt dt. Well, that was 1. Minus v over c squared dx dt. Okay, yes, in case I didn't say it before, derivatives work like this. You can divide dx by dt as long as they're physical and they're normal and they don't have, what is the word I'm looking for? As long as they don't have discontinuities, which physical quantities generally don't. Okay, so we can therefore see that the Lorentz transformation gives us that u prime, the velocity of an object measured in the primed frame, is equal to u minus v. That's what we saw for the Galilean transformation, but it's modified by a fraction 1 minus v over c squared times u. Okay, so there you go. Notice again, so it's a little bit more complicated than expected, but notice if v is much, much less than c, and we can take the 0th order approximation of the bottom, of this fraction, this is small compared to 1, and we get back the Galilean transformation. Okay, all right. So but there is another wrinkle to this. Okay, and that is that look at y prime and z prime. Remember, y prime equals y and z prime equals z. Therefore, dy prime dt prime equals dy dt prime. U prime does not equal u in the y direction, right? So that's the u sub y. So the components matter. That's what I'm trying to say, is the components matter. So this is true, the boxed equation is true if we're in one-dimensional motion. But if we're in two-dimensional motion, this is the x component of the motion. So u sub x prime, we found, was equal to u sub x minus v over 1 minus v over c squared u sub x. But what about u sub y and u sub z? Well, we have to do the same thing. Since dy prime equals dy and dt prime, in order to get that, we got to go back and see that dt prime equals this. So dt prime equals gamma times dt minus v over c squared times dx. So therefore dy prime equals dy over that, dy prime over dt. So therefore u sub y prime is equal to dy over gamma dt minus v over c squared dx. This is really interesting, that the velocity in the y direction, the component of velocity in the y direction, depends on something about the x direction, because the x direction is the motion of the direction of motion of the moving inertial frame, right? But so the y velocity is impacted by the motion in the x direction. That's really important. The y velocity is impacted by the motion in the x direction. We can simplify this and say that, remember again, this was for the x direction. Let's see what it looks like for the y direction. Uy prime is equal to, we can divide top and bottom by dt so that we get u sub y over gamma times 1 minus v over c squared dx dt, which is u sub x. So the x component goes as ux minus v over 1 minus v over c squared ux. The y component goes as uy over gamma times 1 minus v over c squared times u sub x. And the z component better be the same, right? Z component is going to be u sub z over gamma times 1 minus v over c squared u sub x. Okay, so that's a big difference with the velocity transformation.